Welcome back to The Explainer. Today, we're tackling a question that is so fundamental, so basic, that we almost never even think to ask it. Think about it. Pretty much all of science kind of takes for granted that stuff, lasts. Stars, cells, you name it. We just assume they'll be there long enough for us to study. But what if that's the wrong way to look at it? What if the real question, the one we should have been asking all along, is why does anything persist in the first place?
Yeah, most theories show up late to the party, right? They start analyzing things once they're already nice and stable. But today, we're rewinding the tape. We are going all the way back to the beginning to ask, from the ground up, how is it even possible for something to stick around?
I mean, look around you. Your desk, your chair, they seem pretty permanent. But the core idea we're exploring is that this persistence is actually the exception, not the rule. It's a real mystery. Why doesn't everything just fall apart into total chaos? That's the puzzle we're trying to solve today.
Okay, so how do we even begin to tackle a question that big? Well, the approach here is super clever. Instead of trying to build some massive, complicated theory up, we're going to do the opposite. We're going to use logic to just eliminate what can't be true.
It's called constraint-based elimination. And honestly, the best way to think about it is like a sculptor. They've got this big block of stone, right? They're not adding anything. They're just chipping away all the pieces that aren't the statue. What's left over, by necessity, is the statue. That's exactly what we're about to do.
So here's the game plan. It's really just a few steps. First, we imagine every single possibility. Then, we apply a rule, a constraint, something that has to be true. Then, we just get rid of everything that breaks that rule. The beauty of this is that whatever's left isn't just a good guess, it's a logical necessity. It's what has to be true for things to last.
Okay, theory time is over. Let's actually do this. We're going to apply our very first constraint and see what happens. You're about to watch reality get forced into a specific shape just based on logic.
So let's start with a really simple idea. Could a universe of perfect uniformity actually exist and, persist? Imagine it, a state of absolute, total sameness. No differences, no contrasts, nothing. Just beige everywhere. Could that last?
Well, the logic says, no way. For that perfect sameness to hold, any little hiccup, any tiny deviation would have to be corrected instantly and perfectly. But that's just not how the world works, right? Any action, any correction takes time and costs energy. There's always a delay, always a price. You can't just snap your fingers and make it perfect again.
And that's our first big takeaway. We've just eliminated perfect uniformity. So what's left? Difference. For anything to persist, it must contain difference. It's not a choice. It's not a random feature of the universe. It's an unavoidable consequence.
All right, fine. So difference has to exist. But can't you just get rid of it? A difference appears, and then something else comes along and cancels it out perfectly. Boom. Back to stillness. Why isn't that possible?
Well, it's for the exact same reason we talked about before: delay and cost. That correction doesn't happen instantly. It's always a little bit late. And because of that delay, it can't ever perfectly cancel out the original difference. There's always something left over, a little residue. And that leftover bit, that's the engine. That little residue forces the next change to happen. And that change leaves its own residue, which forces the next change, and on and on and on. It's a never-ending cascade. And what do we call a never-ending cascade of change? Motion. So just like that, we've eliminated stillness. Motion is unavoidable. Okay, let's take a breath. Look at our chain of logic. Persistence demands difference, and difference demands motion. We're building something here. So the next obvious question is, okay, what kind of motion are we talking about? Not all motion can last forever, right?
When you boil it down, there are really only three possibilities. Any kind of motion is either going to be settling down towards some final state, or it's going to be exploding outwards, growing uncontrollably, or it's going to be something that reverses direction, going back and forth. Time to pull out our elimination tool again.
First up, monotonic convergence. That's just a fancy way of saying settling down to a perfect balance. Can this persist? Nope. Remember our old friends delay and cost? Any attempt to correct a path toward a target is going to overshoot or undershoot. It's like trying to perfectly park a car with a 5-second delay on the steering wheel. It's just not going to happen. Convergence is eliminated.
Okay, what about the opposite? Monotonic divergence. Just growing and growing and growing, spiraling out of control? Well, that's a non-starter too.
You'd need an infinite amount of energy to fuel that kind of runaway growth. Any real-world system would just burn itself out and collapse. So divergence is out of the picture.
And this is where it gets really cool. This is the power of this method. We've ruled out stillness. We've ruled out settling down. We've ruled out blowing up. So, what's the only thing left? Oscillation. The only kind of motion that can persist is one that constantly overshoots, corrects, and changes direction. It's the only game in town.
But hang on, just wobbling back and forth isn't enough, right? I mean, that explains why things keep moving, but it doesn't really explain how they stay coherent, how they hold their form. It turns out, for something to truly persist, there's one more piece to the puzzle, and this one is a little mind-bending. Okay, check this out. Imagine you have two identical objects. To your eyes, they are exactly the same in this one instant. But what you don't know is that one of them got to this state after a nice, calm, gentle history. The other one, it got here after being shaken violently. Even though they look the same right now, how do you think they're going to behave 1 second from now? Completely differently, right? This proves that just looking at a snapshot of the present isn't enough. Its history matters a lot.
And this brings us to a really beautiful idea called trace. This is absolutely key. Now, don't think of trace as memory, like you have on your computer. It's not information that's stored and then read. It's much deeper. Trace is the physical change to the system itself, caused by what happened to it in the past. It's an irreversible deformation that literally changes how the system is going to behave from now on. Here's the perfect way to picture it. Imagine rain flowing down a muddy hill for the first time. It creates little paths, right? Tiny channels. Well, the next time it rains, the water isn't going to flow randomly. It's going to be guided by those channels that were already carved. Those channels are the trace. The hill hasn't remembered the rain. The hill itself has been physically changed, and that change now dictates the future.
Okay, let's put it all on the table. We have difference. We have motion in the form of oscillation, and now we have trace, this physical imprint of history. So what does persistence actually look like when we combine all of this?
And here's the big reveal. According to this logic, something persists not because of what it looks like in any one snapshot in time. No, it persists because of its entire journey through time. Persistence isn't a property of a state, it's a property of a trajectory. It's the whole movie, not just a single frame, and that movie is directed by its past.
I mean, just look at the chain of logic we built. It's incredible. We started with almost nothing, just the simple requirement that things have to last. And from that one single demand, we were forced to conclude that reality must have difference, it must have motion, that motion must be oscillation, and that it must have a form of physical memory, a trace. These aren't just weird quirks of our universe. They are the logical price of admission for existence itself.
So, I'll leave you with this final thought to chew on. If any system that manages to persist from a rock to a star must have this physical memory, this trace, baked into its very structure just to survive, then what does that say about something like intelligence? Maybe it's not some magical thing that appeared out of nowhere. Maybe, just maybe, it's a highly complex version of a fundamental requirement for existence itself, something that's been woven into the fabric of the universe from the very beginning.